Hi everybody, we are in section 11.9 talking about representations of functions as power series. So we introduced in the last section the concept of a power series, and here we're going to start looking at how we can work with functions, interpreting them as power series, and kind of how that's going to be useful for us. So what we're going to look at first here is the series, just the series of terms x to the n power, with n going from 0 to infinity. So that's just the series, right? 1 plus x squared plus x cubed, etc., etc., etc. Now this may not look like it just on the face of it, but this is actually a geometric series. So it's a geometric series with a equal to 1 and r equal to x. So if you go back and look at the general form of a geometric series, you'll see that it does match that form. So we're using a is 1 and r is x, and we know that if the absolute value of r is less than 1, it's convergent. And since r is x, the absolute value of x being less than 1 means that it's convergent. So this formula for a geometric series that we have gives us this expression right here. So we have the sum from n going from 0 to infinity of x to the n can be written as 1 over 1 minus x. So a really nice, concise formula here for this geometric series. But in this section, we're going to be shifting our perspective a little bit. We're not going to be looking at a series and trying to create a function for it. We're going to be using a function and then trying to find a series to match it, basically. So our perspective is going to be going the other direction. So we can express a function 1 over 1 minus x as a sum of a power series. So we start with the function. We can write that as an expansion of a power series, right? Or use the summation notation if we prefer. So you'll find in this section a lot of the stuff we're doing just builds on itself. So the information that we get from one example is going to help us solve the next example and the next example, etc. So let's look at some of these. So express the function 1 over 1 plus x squared as the sum of a power series and find the interval of convergence. So I'm going to try to relate this to the one that we were just working with, right? 1 over 1 minus x. So if we replace x with negative x squared, we're going to get the following. So we get 1 over 1 plus x squared. That equals 1 over 1 minus negative x squared. Okay, so that's equivalent to the one that we started with. This we can write out in summation notation, so n going from 0 to infinity of negative x squared to the n. So you can see hopefully how we're kind of matching the form here, right? So if we have 1 over 1 minus x, in this case x is just negative x squared instead. So we're using that same form, that same geometric series here. Okay, and then this we can just write, so n going from 0 to infinity. This is negative 1 to the n times x to the 2n. Right, which if you were to expand it out a few terms, you'd get 1 minus x squared plus x to the 4th minus x to the 6th plus etc., etc. Okay, so that's what this series would look like. So that's how we can write the function 1 over 1 plus x squared as an infinite series. And then because this is also a geometric series, so because this is a geometric series, it converges when we have, I'll do this over here, it converges when the absolute value of that quote-unquote r term is less than 1. So when the absolute value of negative x squared is less than 1, which is just when absolute value of x squared is less than 1, which only occurs when the absolute value of x is less than 1. Okay, so this gives us our interval of convergence. So we can say thus, the interval of convergence is negative 1 to 1. Okay, so using information that we have from the previous example, and then just kind of twisting it a little bit, just manipulating it slightly to get it into a form that we can work with using what we already know. Okay, let's look at another one. So find a power series representation for 1 over x plus 2. Okay, so what we can do is I'm going to factor a 2 out of the denominator. Okay, so 1 over x plus 2. I'm going to go ahead and, first of all, I'm just going to switch the 2 and the x, so 1 over 2 plus x, because that's going to match the form a little better. Oops. Okay, factor out a 2. So 1 over 2 times 1 plus x over 2. And why would we do that? Well, because we need it to look like 1 over 1 minus x. Alright, so I'm going to need to get a 1 here, which we just did. And now we're going to need to get the minus x, which we're going to use a trick similar to the one we did on the last one. So this we can go ahead and rewrite. So 1 over 2 times 1 minus negative x over 2. Okay, so this now has the proper form. So let's get the 1/2 out of there. And if you just for a second ignore the 1/2, that has our geometric form that we need. So sum from 0 to infinity of negative x over 2 to the n, which we can rewrite just to condense it. I can go ahead and bring the 1/2 back in, distribute that nth power to all the terms, so we've got negative 1 to the n over 2 to the n plus 1. It's n plus 1, again, because I'm bringing in that 1/2 back into the sum. And then that whole thing times x to the n. Alright, so that's going to be our power series representation for that expression, 1 over 2 plus x, or 1 over x plus 2. If we were wondering about convergence, so this converges when absolute value of negative x over 2 is less than 1. So when absolute value of x is less than 2. Thus, the interval of convergence, which it didn't ask for in this case, but might as well get the practice of finding it. That is negative 2 to 2. Alright, so there we go. So again, let's try another one. So find a power series representation of x cubed over x plus 2. So first thing we want to notice about this function, so this function, we can rewrite it and just get that x cubed out of here. That's x cubed times 1 over x plus 2. So notice that that's the second part of that, the 1 over x plus 2, that's just the same thing that we just did. right? We found a power series representation for that one. So really, all we need to do is just multiply the series by that x cubed factor, and then that's going to give us what we want. So we can just multiply the series. Okay, so x cubed over x plus 2, and that's x cubed times 1 over x plus 2, which is x cubed times the sum that we got up above, so the sum n going from 0 to infinity, negative 1 to the n over 2 to the n plus 1 times x to the n, okay, which is, we can go ahead and bring in the x cubed in there. We can do that because it can move inside and outside of the sum because it doesn't have an n in it, because n is treated as the variable of the sum. So we have the sum n going from 0 to infinity of negative 1 to the n over 2 to the n plus 1 times x to the n plus 3, okay, which we could write out a few terms. That would give us 1/2 x cubed minus 1/4 x to the 4th plus 1/8 x to the 5th minus 1/16 x to the 6th plus etc., etc. Okay. So we could also rewrite this series in a different way. So that's our series there, but we could also rewrite this series as the following, because sometimes we like to make our work look a little more consistent in terms of our powers on x. So we can write this as x cubed over x plus 2. That would be the sum n going from 3 to infinity. If we start at 3, then that shifts all of our powers down, so this becomes n minus 1 over 2 to the n minus 2 times x to the n. Okay, so we could write it that way. And then this one, because we just manipulated by multiplying by the x cubed, the interval of convergence is going to be the same as the other one. So we didn't change the interval of convergence by applying this multiplication. Okay, so the interval of convergence is similarly negative 2 to 2. All right. Now, one of the reasons that we want to be able to work with power series in this way is because we can work with calculus using power series. We can use differentiation and integration for power series, and we would use what we call term by term. So term by term differentiation and integration with power series, as we would with polynomials. Power series create basically infinitely long strings of polynomials, and we can do calculus on polynomials fairly easily. This is why we like working with power series. So here we have a theorem. So if the power series has radius of convergence r greater than 0, then the function f, defined by that expanded power series here, okay, is differentiable and therefore continuous on that interval wherever it's convergent. Okay, so this also tells us that f prime of the function, okay, is just going to be the derivative of each term of the power series, and the integral of the function is just the antiderivative of all of the terms of the power series. Now, writing these out in summation notation, let me just put that in here. So that's going to be the sum n going from 1 to infinity of n times the coefficient c sub n times x minus a to the n minus 1. Okay, so hopefully that looks kind of familiar, right? Bring down the n and subtract 1 from the power. That's just the power rule. And the integral would just be c, an arbitrary constant, plus the sum with n going from 0 to infinity of coefficient times x minus a to the n plus 1 over n plus 1. So, and hopefully that formula looks familiar. That's just undoing the power rule, right? How we take an antiderivative of the power rule. So the radius of convergence of the power series for both of these is still r. So by differentiating and integrating, you are not changing the radius of convergence. So a note here, we know for finite sums, the derivative of the sum is the sum of the derivatives, and the integral of the sum is the sum of the integrals, right? You can split up derivatives and integrals across addition and subtraction. That's what that tells us. But this theorem also tells us that that is true for infinite sums as long as we are dealing with power series. So as long as we're dealing with power series, we can split up all of this infinite string of terms in the series and differentiate each one individually and integrate each one individually. Okay, so that's what this basically says down here. The derivative of the sum is the sum of the derivatives, and the integral of the sum is the sum of the integrals. All right. Let's look at an example. So express the function 1 over 1 minus x quantity squared as a power series by differentiating the equation from the beginning of the section. What is the radius of convergence? So we started off in the section talking about 1 over 1 minus x, which was 1 plus x squared, etc., which is just the sum, n going from 0 to infinity of x to the n. Okay. So if we just differentiate all sides of this, so the derivative of 1 over 1 minus x is 1 over 1 minus x squared, or excuse me, 1 over 1 minus x quantity squared. There we go. Differentiate each of these terms in here individually. So you get 0 plus 1 plus 2x plus 3x squared plus etc., etc. Okay, and then differentiating the sum, we go n from 1 to infinity of n times x to the n minus 1. Because if we let n start at 0 with this one, it's not going to work, and it just gives us a 0. Right, in that coefficient position, so it's not going to contribute to the sum at all. So we just start at 1. Okay, so that gives us a power series representation for that function. We could also replace n with n plus 1. To get the following series. So to get 1 over 1 minus x quantity squared equal to sum n going from 0 to infinity of n plus 1 times x to the n. So if you wanted n to start at 0 and you wanted to have x to the n as your power there, then you could just basically shift the whole thing down, okay, by starting using n plus 1 instead of using n. Okay. The radius of convergence, like I mentioned, of the differentiated series is the same as the original. So r equals 1 is still the radius of convergence. Okay, so that is unchanged. All right. Let's look at this next one here. Find a power series representation for ln of 1 plus x and its radius of convergence. So, good thing to notice here. So notice that the derivative of this function, right, of the natural log function here, the derivative is 1 over 1 plus x. And that's something that we can work with, right? So we have 1 over 1 plus x equals 1 over 1 minus negative x, right, if we want to put it in that geometric form. So this would give us 1 minus x plus x squared minus x cubed plus etc., as long as the absolute value of x is less than 1. And then what we can do is we can integrate. So go with something we know, and then manipulate it to get it to something that we want. So here we have ln of 1 plus x. That is the integral of 1 over 1 plus x dx, which is the integral of 1 minus x plus x squared minus x cubed, etc., dx. Okay, so take the antiderivatives of all of those, just one by one. That's going to give us x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc., plus c, plus that arbitrary constant. Okay. Now, we can go ahead and find c, just really quickly here. So, find c. So, when x equals 0, look at kind of that initial value, that initial case. When x equals 0, we have ln of 1 plus x, or excuse me, 1 plus 0, which is just ln of 1, right, equals c. So c equals 0. Okay, so that's pretty useful, just to get c taken care of there, just get it out of the way. So this gives us just x minus x squared over 2 plus x cubed over 3 minus etc., just onward forever. Okay, and then just plus 0 because of that c. And then we can even write the summation notation here. Just n going from 1 to infinity of negative 1 to the n minus 1 times x to the n over n, with the absolute value of x being less than 1. Okay, so that's going to be our power series representation. And again, because we are integrating here, and we already knew the radius of convergence was 1, in this case, r is still 1. Okay, so that is unchanged. R is still 1. Alright, and let's look at one more. So find a power series representation for the inverse tangent function. So observe. So you'll notice a lot of these problems start off with, right, our observations of how these functions relate to the other ones that we've used so far. So this is the derivative of inverse tangent. So we can use that and integrate the power series. Okay, so we have inverse tangent of x, that is the integral of 1 over 1 plus x squared dx, which is the integral of 1 minus x squared plus x to the fourth minus x to the sixth, etc. dx. So that's going to be c, arbitrary constant, plus x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus etc. etc. So it looks like we're getting all of the odd powers on x, okay, and then divided by that same number. We can find c really quickly. So when x is 0, c is just inverse tangent of 0, which is 0. So this isn't to say that c will always be 0, it just happens in these two examples it has been. So this just gives us x minus x cubed over 3 plus x to the fifth over 5, etc. Okay, which we can write using the summation notation. That's going to be the sum, and going from 0 to infinity, negative 1 to the n, because it's alternating, times x to the 2n plus 1 over 2n plus 1. So that guarantees that we will get that next odd number in the power and in the denominator of the fraction. Okay, and then of course the radius of convergence is still 1, because that remains unchanged from the original series that we were talking about. All right, so that's kind of our discussion. That's it for the section. So that's our discussion on how we're representing functions using power series. When we come back in the next section, we're going to look at some special types of series that we're going to be working with, and how those can directly apply to a lot of what we're doing here, including performing calculus operations. So I'll see you back for that next section.